I'm talking about joint work with Mark Jampapa, and it is about the possibility of enhanced stellar activity at slow rotation, which we expect to be anti-solar-like. We have seen that as we compare stars of different rotation periods, as the rotation period becomes longer, the activity here measured in X-rays decreases. So slow rotation, decreasing activity. We normalize normally the rotation period by the convective turnover time. This is the empirical noise turnover time. And this allows us to compare in one and the same plot different stellar types, K-dwarfs, G-dwarfs, and so forth. But what happens as we go toward even slower rotation? You see there is not many stars in this point. So this is why it is new. Nobody has really studied this in depth yet. Is it true that there is something like a basal flux limit at some point? We don't see anything like this here. Or is there maybe no flux at all? Or is there some new effect? So this is the subject of today's talk. And there are some curious findings related to this, which came about when Mark Jampapa contacted me last summer with a plot like this, which shows, again, the Rossby number. The rotation period becomes increases in this direction, so it becomes more slowly rotating, again, normalized by the convective turnover time. But as we see here, RHK prime, our most important activity indicator, actually increases with slower rotation, just the other way around than what we have seen just before. So what is wrong? There are some stars. The difference here is these are the more lighter stars in the sun. These are the somewhat more active, heavier stars in the sun. But by and large, you might see something like completely the unexpected trend. So these are data that have been obtained from the Kepler K2 mission. About 20 stars or something like this have been accurately determined. RHK prime has been determined with the Windens 3.5 meter telescope at Kidd Peak. And what we see here is this increased activity with increasing Rossby number. Is it perhaps that the rotation periods are wrong systematically? Or is it that some of the stars are evolved stars? But we'll come to that, or can come to that, in looking at this color magnitude diagram. That is actually not the case. Is it that perhaps as the large-scale dynamo becomes weaker, the small-scale dynamo responsible for spots becomes stronger? Nothing unusual that we expect, actually. Or is it that the differential rotation, which is importantly responsible for creating activity, actually becomes stronger for slower rotating stars? If we look here at the residual between the RHK prime and the inverse Rossby number, tau divided by p rod. So if the activity scales linearly with the inverse Rossby number, then we expect this to be a flat line. And indeed, you see here for different RHK prime, we have a flat distribution. So this means that all the stars from the Mount Wilson sample are falling on a linear line of activity versus inverse Rossby number. And now we will add to this the stars of M67. And so you see here, all the stars of M67 deviate systematically from the expected flat distribution. And so this really shows us that stars that become more slowly rotating, they go up further up here, become more active. So is there a way of understanding this in a physical way? And also, is this some phenomenon that is actually real and can be seen in other field stars, of which we don't have so many, unfortunately, yet? So before I come to the explanation, let me explain what we do expect from theoretical models for slow rotation. And this is known since the work of Gilman, 1977. As stars slow down, they become antisolar differentially rotating. That means that unlike a star like the Sun, where the equator is fast and the poles are slowly rotating, as we go to slow rotation rates, we will have an equator that is slowly rotating, and a pole that is had higher rotation speed. Not only that, so this means we have a change in sign. Here's 0, here's a latitudinal differential rotation. As we slow down in rotation, we all of a sudden flip the differential rotation and it becomes stronger. These are hydrodynamic models, and the same is true in magnetohydrodynamic models. And now I'll show you what looks like the actual, and this is from a simulation here by Karak, the same simulation of which I showed you earlier the pictures. As we get more slowly rotating, we turn the differential rotation into antisolar differential rotation, and it becomes stronger. Differential rotation becomes stronger, and the activity, BRMS, increases. And now we compare in a combined plot both the Mount Wilson stars in the different colors, K dwarfs and H dwarfs, and we see that the activity really falls on a continuous line where all of a sudden the activity increases. What if the rotation periods aren't actually accurately determined? Well, there is a method of estimating, because we know M67 has systematically an age of approximately 4 gigayears. And so based on just measuring B minus V, even if you don't trust P rotation at all, you get a computed P star rotation period, which actually gives the same kind of representation. So this gives us confidence that this result is actually not an artifact. Regarding field stars, there are a few field stars, especially up here, but there aren't many. And so I think in future it will be really important to get data for many more stars. How does it all fit into context? So we have seen as stars slow down, they slow down because of magnetic braking. They become also less active, and there will be even less braking. And so one possibility out of two possibilities is that those stars will remain rapidly rotating and become simply older. But there is another possibility. Some stars may actually become antisolar differentially rotating. And so all of a sudden they generate again strong differential rotation, and even stronger so than before. And so all of a sudden the star has a revived activity and becomes even more active. And that is what I'm proposing here. It is, of course, important to check this in future, perhaps using light curves and perhaps using astroseismology. There's another possibility also that has to be considered here, and that has been brought up in a paper by Katsova recently, that some of the superflaring stars that have been seen with Kepler might actually be just stars like the Sun, but they have already turned antisolar-like, and may be an example of displaying extremely strong differential rotation and therefore superflares. So there's a great wealth of interesting possibilities if we can only determine whether some of the stars are antisolar differentially rotating. Thank you.
Thank you very much, Axel. I mean, you didn't even use up your time, so there is time for questions. Ansgar?
Ansgar Reiners from University of Göttingen. Axel, nice work. I have one comment with a question. So I'd like to remind ourselves, everyone, that the use of the Rossby number is motivated by the saturated part of the rotation activity relation. And the non-saturated part works without the Rossby number. I'm not making any argument about whether that's better or worse, but I'm my question is, did you look into your stars and just not normalized activity versus period? Does that show the same
So
relation?
you have seen here the different colors. If I were to not use the Rossby number, you would see a strong segregation between the red stars and the blue stars. And so it is not true then, in that respect, that you can forget about the normalization by tau. I'm not convinced, I don't think so. This plot would at least not look nice anymore.
Elizabeth Newton, MIT. Can you comment at all under your antisolar differential rotation scenario? Do the rotation periods continue to decay, get longer? Unlike, that would be like I'm wondering if there's a very different prediction with respect to rotation period as compared to the von Seder's hypothesis.
You talk about K dwarfs, you mean? What do you mean? Can you repeat again? Continue to what?
In you predict two scenarios. You propose there might be two scenarios for what happens at Rossby number equals 2, with respect to and
right.
This plot discusses the activity of the star, and I was wondering if beyond this there was a difference in the rotation period evolution. So in the von Seder's proposal, they would stop spinning down. Under this scenario, would they continue to spin down, or would they stop spinning down?
So you're talking about younger stars.
Just at Rossby number of 2, but we could discuss this later.
Yeah,
as
let's
well.
discuss later. I didn't quite understand.
Mansour Benbakoura, grad student at CA Saclay, for maybe a naive question on how do you actually measure the convective turnover timescale? I've seen different papers and different
It's a noise relationship,
results.
so it's really just B minus V. So B minus V translates into a tau. That's what we use. And it should work okay as long as we have main sequence stars.
Hi, Rick Egelin from High Altitude Observatory. How confident are you in the activity measurements, and are there any other measurements for these stars that give you additional confidence?
Does Mark have a response on that?
Yeah, they're moderate resolution spectroscopic measurements. So it's about between 0.8 and 0.9 angstrom resolution, and so I just adopt the index in that 1 angstrom core of the H and K lines, and the distribution compares favorably with my previous 2006 survey. So I'm fairly confident in that. The photospheric contribution is determined again with a noise relationship as a function of B minus V color, so that's used to derive the R prime HK.
Keyboard on the other side, yeah.
Jim Davenport, University of Washington. So this would seem to make a prediction that older stars should be more active than we expect, and so we need to do a survey. Are you suggesting we need to do an activity survey of K dwarfs at like 3 kiloparsecs above the plane? Because you need some other indicator of inferring their age. Is there a better way to go after this?
I mean, the age is a secondary thing, but yeah, we do need to look for stars that have at least slow rotation periods, large Rossby numbers, larger than 2.4. Maybe 2.6, and even larger. And
Yes.
Activity. And we also expect there to be a large spread. It's not that all of the stars will become active. There will also be a larger spread. That is also theoretically expected. It's in our paper.
Well,
Sorry, Igor?
Gibor
yes,
Basri,
okay, then.
Berkeley. So I'm just to finish this topic, which was started by the question a while ago. I think it's really a very important point of what you're proposing. The question is, if the stars become more active when they reach Rossby number 2, will they then begin to magnetically brake harder and thus slow down? That's the question.
They will slow down. However, the way in which they will slow down is also much more chaotic. So there will be maybe periods where they will slow down and other periods where they will not slow down, because we don't have regular butterfly diagrams anymore. It's much more chaotic at the time.
Okay, last question.
Eric Mamajek, JPL. Thank you for calling on me.
Well, a difficult
Quick
to spot
question.
in the back.
Not even a comment, a question. Oh, observationally, how do we test your bifurcation scenario for anti-solar rotation? Thank you.
I mean, observationally, that's what we have seen. And it does, if you want to explain it somehow, you have to explain it with some kind of a bifurcation scenario. So I think these are just the observations. And we just have to fill in more data points. So bifurcation means not all of the stars will be lying on this line. There will be a spread. Some of the stars will be actually ending down here. Like, for example, Alpha Centauri A, which is, I think, this one here. Alpha Centauri A and a few other such stars, they will become just simply active as a rapid rotator. So they will just go down vertically. But other stars will go up in this direction. That's the interpretation, the proposal. And now the game is to determine, to verify antisolar differential rotation, which has so far only been seen for subgiants and giants, not for main sequence stars.
Okay. Thank you very much.
Thank you.
This concludes the session and the discussion. I thought it was a very lively discussion. And don't go away.